alkyls of such organometallic compounds. So here we know that transition metals particularly, they are very prone to form organometallic complexes. It is because of the presence of the vacant d orbitals and also because of their sizes, which allow to take up various types of ligands. So here we will first start with the transition metal. Particularly in this context, we will talk about the transition metal alkyls and aryls. So here the main group elements, that is particularly lithium, magnesium, zinc, mercury, arsenic and aluminium, they form the first metal alkyls, of which still some are in use. Particularly when we alkyl lithium reagent, it is the starting point of many organic synthesis. This alkyl lithium is not only helpful in the synthesis of different complex organic molecules, but also it is found in a variety of reactions in analytical complexes. So here diethyl zinc, it is also considered as the first true molecular compound which has a metal carbon bond, the for which Franklin is considered as the founder of the organic organometallic chemistry. Diethyl zinc is that was the first organometallic compound to be established showing the from the XRD data to be showing the metal carbon bond. It was also with the discovery of the alkyl magnesium halide reagent, that is we call the RMGX, that is commonly called as the Grignard's reagent. So we know that this Grignard's reagent is particularly used in or various types of organic synthetic reactions. And then Slenk and Ziegler, they helped in developing organolithium compounds and also organoaluminium compound reagents. They have also been found by the by Ziegler, and they are common called as the Ziegler-Natta catalyst. So these are some of the organometallic transition metal alkyls and aryls that are found and that are also in use in various types of reactions that find use till today. So coming to the types of organotransition metal alkyls and aryls. So organotransition metal alkyls and aryls, they have been broadly classified in on different bases. So first classification is based on the types of ligands they that is present. So the based on the type of the ligands, we have classified the organotransition metal alkyls and aryls as homoleptic or heteroleptic metal hydrocarbyls. So what is a homoleptic? So homoleptic are, that is MRN. These are those hydrocarbyls where all the organic groups on the metal atom, they remain the same, and that is why they are called as the homoleptic. Like for example, tetramethyl titanium. So when we look into tetramethyl titanium, the central metal atom is titanium and four methyl groups are surrounding it. So the since the four methyl groups, they are same on all sides of titanium, then such type of complexes is a homoleptic metal hydrocarbyl. Then also we have hexaphosphine vanadium. If you look here, this is also a homoleptic hydrocarbyl. Also heteroleptic hydrocarbyls are present where to the central metal atom different substituent groups are present. Like for example, if we have titanium M methyl group 4 minus X and any ligand Y. Also we have zirconium dimethyl dicyclopentadiene. If you look into this complex, zirconium is the central metal atom, two methyl groups are there and two cyclopentadienyl groups are also attached to it. So here we call it as a heteroleptic metal hydrocarbyl. So this is how the classification of the organotransition metal alkyls and aryls have been done on the basis of the types of the ligands that is attached to it. Then in the second case, on the basis of the nature of the ligands, they are also classified into, we call them as alkyl organometallics or we call them aryl organometallics. So organometallic compounds with the alkyl radicals, they are called as alkyls. Like the common example is tetramethyl titanium. So here it contains an alkyl group. So for alkyl group, that is the methyl groups, they are attached to titanium. This is also a homoleptic compound and this is also an alkyl organometallic. Also you can see hexamethyl tungsten. So here this is also homoleptic in nature, and it is also called as a alkyl organometallic. But when we have any organometallic compound wherein aryl radicals are present, then we call them as aryl organometallic compounds. Like for example, here we have lanthanum phosphine, lanthanum tetraphosphine ion, here it is given. So lanthanum, then four phosphine groups are added, and we know that so no, this, sorry, this is tetraphenyl lanthanum. So here four phenyl groups, they are attached to lanthanum, and that is why they are called as aryl. Since phenyl is a aryl group, so that is, so we call this as aryl organometallics. And other examples here have been given. These compounds have also been classified as symmetrical, like tetramethyl zirconium, or we can call them as unsymmetrical, like butyl trimethyl titanium. Or we also have mixed, that is which contains an alkyl aryl heteroligand, like here it has been shown here. So this is how alkyl and alkyl organometallics, aryl organometallics, and we also have symmetrical, unsymmetrical, and mixed organometallics. Then the organo transition metal alkyls and aryls have also been classified based on the number of the metal atoms that is present in the complex. So if it contains, they are called as mononuclear or polynuclear. So when in polynuclear metal organometallics, the metals are linked together, that is either through bridging bond or directly with through the single or double bonds. Also there is a metal metal bridging alkyl or aryl are also present. So this is the three simple classification of the type of organotransition metal alkyls and aryls based on the nature of the ligands, based on the alkyl or aryl group that is attached to the ligand, and also based on the number of the metal ions that is present in the complexes. That is either it can be a mononuclear complex or it can be a polynuclear complex. So this is the a brief introduction to the classification of the organotransition complexes. Then coming to metal alkyls as stabilized carbanions. So we know that electrophilic alkyl groups, they are available mostly from the alkyl halides, and the nucleophilic alkyl groups, that is the R delta minus, they were first found in the Grignard's reagent, that is RMGX. So the metal alkyls, they result from combining an alkyl anion with a metal cation. So as a result, what happens, the alkyl anions, it gets much more stabilized, and this stabilization, it depends upon the metal ion that is present in the complex. So here when we talk of the metal alkyls, here the alkyl anion, since we are talking of the organometallic complexes, the alkyl anion, that is R delta minus, it is stabilized, it is, and the stability of this R delta minus, it depends upon the electronegativity of the central metal ion that is present inside the complex. So polar organometallic compounds from the alkyls of the electropositive elements of group 1 and 2, as well as uh, zinc and aluminium, they, since the alkyl anion is weakly stabilized, and they retain much of the strongly nucleophilic character of the free anion. So the polar organometallics must always be protected from air and water, as they are susceptible to oxidation reactions. This is because the readily hydrolyzable, the MC bond, it forms the MOH bond, that is whenever they are contact in water or they come in contact with air, they undergo oxidation reactions very easily. So alkyls of the early transition metals such as titanium or zinc, they are also very sensitive to moisture and oxygen. So this situation, it changes when we go down the periodic table, where there is less electropositive metals, and as a result the reactivity of such complexes, it decreases. So again the situation changes when we reach mercury. So where the stability of this mercury carbon bond, it makes the methyl mercury plus cation much stable in aqueous sulfuric acid in air. So here in figure 4.9 you can see the nucleophilic reactivity of the main group and transition metal alkyls versus the electronegativity of the metal. So here in this case this is the MCH-3, MC6H5 and MC6CCr. Here the different types of metals where the electronegativity increases in the x-axis it has been shown, and how the nucleophilic reactivity it increases has been plotted here. So in figure 4, this figure, we see the effect of the changing metal, and it is seen that the reactivity drops when we move from sodium, methyl sodium to, when we move from methyl sodium to lithium and magnesium species, then it gradually drops to the, so we must not forget that the stability of the R fragment is also important. This alkyl group has an sp3 ion, and we know that CH3 minus is most reactive. So when the orbital has more of S character, that is sp2c6h5 minus, and even more sp, that is Rc triple bond C, then the lone pair of the ion it is stabilized. Once the lone pair is stabilized, so the reactivity decreases. So similar trend also makes the hydrophobicity of the hydrocarbons. We have the pK of methane is approximately 50 to the pK of benzene almost 43, and that of Rc triple bond C is 25. So here this makes the anion most stable and least reactive. Then it was first Pope and Peaches, this complex Me3PTI, who looked into the polarity and the stability of the different types of anions, and they related it to the stabilization of the metal complexes. So they are, so what happens is, so the transition metal alkyls they decompose easily, and so they could not be the synthesis is difficult, but they decompose easily. Thus the reaction kinetics, they are responsible for the synthetic failures. So there has to be some ways to be found so that decomposition can be blocked. Now since these metal alkyls are very much susceptible to decomposition, so there were, one has to find out different ways how the decomposition can be stopped. So one method, one important method of stopping this decomposition is called as the beta elimination. So beta elimination, here it is given explained in this figure 4.4. So what is this beta elimination? It converts a metal alkyl into a hydridometal alkene complex. Then this hydridometal alkene complex it decomposes for the and forms the respective alkyl. So what happens here is this mechanism happens when there is a hydrogen substituent in the beta carbon of the alkyl. The beta hydrogen it comes close to the metal as the MCCH unit can take up a coplanar conformation. Then there is a vacant site on the metal which is cis to the alkyl. The reaction is faster for D2 and higher metals, and D0 and main group metals C. So in this reaction, the beta hydrogen of the alkyl group, that is, it is transferred to the metal. So here you can see how the beta hydrogen with the help of beta elimination, in particularly in this complex, it is transferred to the metal and it gives the product hydride. So here the hydride product is formed, so the points 1 and 3 arise. Then the metal it acquires a cis position. This is always mandatory that the vacant site of the metal it will always appear at a cis position, and the ligand should have a coplanar MCCH arrangement. Here if you can see, this is MCCH arrangement. Here it has been shown in the intermediate step, it has been shown the CH bond breaking and the MC and MH bond making it takes place simultaneously. Then in the next step both the bond making and the bond breaking it takes place simultaneously. So the vacant site that we have referred to here in the on the metal, on the presence of the vacant site on the metal, it does not mean that there should be some available vacant orbital in the coordination sphere so that any ligand can be accommodated. So beta hydrogen, the pair of electrons that constitute the beta CH bond, it must be accepted by the empty orbital which must be present. So the increases, because of this, this increases the electron count of the product alkene hydride by 2 electrons more than that of the parent alkyl. So whenever it has been found that an alkyl has 18 electron, it would be readily forming a 20 electron intermediate. So if we start with an alkyl which has an 18 electron, then first it forms an intermediate which has 20 electron. In order to, then for the beta elimination process, after it occurs, then it forms a 16 electron alkyl will be resulted. So this is always, it happens that two more electrons extra they are formed in the intermediate step. So here, even if the alkene subsequent dissociates, which we find here, the alkene, this alkene, it ultimately it forms CH2 CH2. We have to stabilize the transition state leading to the alkene hydride intermediate if we want the reaction to be fast. So if we have an 18 electron alkyl, it is said to be coordinatively saturated. So here it means that once it has an alkyl has an 18 electron, so it means that no empty orbital is available. So some, that means if no empty orbital is available, then the molecule, it should not undergo any beta elimination. But some alkyls, 18 electron alkyls, have shown beta elimination, but detailed mechanism or this has not been fully understood yet. So main group elements can also form beta eliminate, but this usually happens very slowly. So this is an example of a main group element which shows beta elimination. The reason for such type of difference is believed to be the greater ability of the D block elements to stabilize the transition states than those involved in the main group element. So mostly beta elimination, when we talk of a beta elimination, it mostly refers to the transition metals rather than the main group elements. Then coming to stable alkyls. So thus blocking the beta elimination pathway, it prevents decomposition and forms an kinetically stable alkyl. So the compounds in which this can happen has been tabulated in table 4.3. So here in this table, some examples have been shown for compounds which form kinetically stable alkyls. So here first is the alkyls that have no beta hydrogen. So here you can see WME6, this is a compound which has no beta hydrogen. Alkyls for which the beta hydrogen is unable to approach the metal as a result of the geometry or bulk of the ligand. Some examples have been given here. There are also alkyls in which the MCCH unit cannot become syn coplanar. So here it has been, in this case ABC, it has been shown here. And 18 electron species, we know that mostly in 18 electron species they do not undergo beta elimination and form stable alkyls, but some common example, a few examples has been known, and here it has been shown in this part, and some D0 alkyls has been given here. This example, it also form a kinetically stable alkyl. So now there is a special case which needs mention, that is the case of WME6. So ML6 species particularly, that is 6 ligands are attached to it. They generally, we know when 6 ligands are attached to a central metal atom, then the resulting geometry is mostly octahedral in nature. But when we talk of WME6 or WH6, they have a trigonal prismatic structure. Now, although the coordination number remaining 6, octahedral geometry is not preferred. Rather, a trigonal prismatic structure has been confirmed from the X-ray studies. Now, Albright and Einstein, they had previously predicted where X is not a pi donor, the D0M6 species, it takes trigonal prismatic shape. The methyl ligand is of the small size, and so polyalkyls are formed with it, and many compounds are formed as a result of this. So stable alkyls are also formed by the substitution with when we have the electron withdrawing groups such as CH2PH or CH2SiMe3. Even though the vinyl and phenyl groups both have the beta hydrogen, they do not eliminate beta eliminate they do not undergo beta elimination easily. So here we see, even if there is vinyl and phenyl groups, in particularly we know in vinyl group and phenyl group there is beta hydrogen, but they do not undergo beta elimination. The beta hydrogens are much away from the metals in these sp2 hybridized systems with 120-degree angles at carbon, now which is not favorable for the delivery of the for the elimination of the beta hydrogen. So this may be the reason for these groups, they do not undergo the beta elimination. Also the phenyl and vinyl groups, they being electronegative alkyl groups, they have stronger MC bonds than that does the ethyl group. So here is the trigonal prismatic structure of WMe6. The isopropyl and tertiary butyl chromium complexes, they are very unusual in nature. Because of the presence of the steric hindrance, it prevents the beta carbon hydrogen bond from reaching the metal. So these metals, they are sterically saturated because they have lot of steric hindrances along the structure. The examples which contain non-coplanar MCCH groups, mainly it involves cyclic alkyls, in which the rigidity of the ring system, it holds the metal carbon carbon hydrogen dihedral angle to 60-degree, and thus much far well, that is, and since they are held, the dihedral angle becomes 60-degree, so beta elimination is not possible in this case. So the fourth group here also involves such type of systems where there is no vacant site, and once there is no vacant site, so these species, they cannot undergo beta elimination. Then coming to the class of agostic alkyls. So what agostic alkyls? So what are these agostic alkyls? So here, so agostic alkyls, they may not occur in species if, even in which all the criteria seem to be favorable, and this is also possible. So in some cases, even though the alkyl starts to be in the transition state for beta elimination and the beta carbon hydrogen bond is bound to the metal in that way, but some way the reaction does not proceed. So the compound here, it has been shown for the X-ray crystal structure and high field shift of the agostic hydrogen in the proton NMR is used to detect the agostic alkyls. So the compound which has been shown here in figure 4.12, so in this compound, figure 4.12, here this is a D0 alkyl. This is a titanium complex, and it has been shown here. It has D0, which does not have electrons necessary for the back donation of the sigma star orbital to the CH bond. So in the beta elimination reaction, this back donation, it breaks the CH bond, and the absence of it, beta elimination does not occur in the compound. So coordinatively, unsaturated species are also stabilized by agostic binding of the CH bonds. So for beta elimination, a 2 electron vacant site must be there on the metal. So additionally, an available electron pair is also required for breaking the CH bond. So these conditions are very much similar to those required to bind soft ligands, that is mostly carbonyl. So carbonyl, both processes require a metal that is both sigma acidic and pi basic, and particularly such binding leads to a reduction in the carbonyl bond order. So we'll gradually read about the metal carbonyls and how these reactions, the carbonyl reactions, they occur very easily with the transition metals which have partly filled d orbitals. Then coming to after beta elimination, it is halide elimination. So halide elimination, beta elimination of the halide can also occur. It is also possible for the lanthanoids and the actinoids, along with some transition metals such as titanium. The very high metal to fluorine bond strengths of these, it encourages the very high metal to fluorine bond strengths of these element. It encourages the beta elimination of the halide. And so because the beta elimination of the halide is preferred, then in the case of, in such cases, fluoroalkyls are not formed. So when stable fluoroalkyls are formed by the late transition metals which have weaker M to F bonds, the beta hydrogens, they are not present in these ligands, and the MC bond strengths are very high. Now this is the case for other alkyls. This is the case for other alkyls such as we have MCH2X. For the pi vesiclate metals, the sigma star orbitals of the CF bond can use the pi acceptor ligand, that is CF3, and thus the MC bond becomes stronger. So an aryl sigma star orbital, it acts as electron acceptor in the aryls with C6F5 group, and stable aryls, they are mostly formed with the higher transition metals. Then is the reductive elimination. So metal alkyls may undergo decomposition by reductive elimination, and often they are, it has been found that they prefer the path of reductive elimination. So both the electron count and the formal oxidation state, it decreases by 2 units. So it is called as reductive. So even if a D0 or 18 electron process undergoes this process, that is reductive elimination, it results, if it results in a stable oxidation state, 2 units will be reduced than the original one. So whatever we start with, my 2 units will always be reduced. So when X in equation 4.7, so this is the equation 4.7, it is a halogen, then reductive elimination is not observed. This is because in this equation the position of the equilibrium, it is towards the left, and so the reactant is more stable thermodynamically. So however, some examples of loss of alkyl halides are known, but when we take X is equal to H, then the kinetically and thermodynamically favorable reaction takes place. So in such a case, it is not possible to isolate the alkyl hydrides. Since we have taken X is equal to H, it is now hydride. So the reaction is generally much slower kinetically. So when we have X is equal to CH3, then the elimination is favored thermodynamically. We know that hydrogen has only one bonding electron in a 1s orbital, so which is capable of making and breaking bonds in any direction in the transition state. Thus, it is found that whenever hydrogen atoms are involved in reactions, there is a much faster reaction than when other atoms are involved. So the overlap in the transition state would be less when there is sp3 orbital of the CH3 fragment. Then stability from bulky substituents. So organometallic compounds of different classes may be stabilized. They are mostly stabilized by bulky ligands. For a 16 electron metal specifically, the alkyls, they can be decomposed associatively when it reacts with the solvent or other molecules of the complex. So in such situation, the bulky co-ligands may be used to stop the decomposition. Suppose we have a square planar nickel to alkyl. So there can be attack along the z direction which is perpendicular to the plane. So now if you look at the orthotolyl complex here, which has been shown in figure 4.14, where the approach is blocked and thus it becomes more stable than the analogous diphenyl, which is shown here in figure 4.5. So this is the orthotolyl and this is the diphenyl, same nickel complex. So the common bulky groups that is found in organometallic chemistry, for example neopentyl or trimethyl silyl methyl, that is CH2SiMe3, they have been used for this because of the steric factor. So even though beta elimination is ruled out in much cases, in certain cases alpha elimination may occur, and particularly whenever alpha elimination is involved, carbene are formed. So what are carbenes? Carbenes are metal to carbon double bonds. For example, when we have titanium tertiary butyl complex which undergo thermal decomposition first, it and then followed by alpha elimination to form this complex. So in the same line, the carbene complex here, it is formed during the preparation of this complex. So now let us see the situation when we have a heteroatom such as nitrogen or oxygen that is present in the adjacent CH bonds, and the that is present and the adjacent CH bonds are activated. Then double CH bond cleavage, they can occur at the same reaction. Here in equation 4.8, if R is equal to H, so here if we take R and that is H, then oxidative addition takes place followed by alpha elimination. Now if we take R is equal to CH3, then alpha elimination or beta elimination takes place in the second step, but only here will beta elimination might occur, but alpha elimination takes place. In equation 4.9, here carbene is the only again form, but the intermediate complex, it results from the hydrogen produced which by the intermediate complex gets form this type of product. So now coming to the preparation of transition metal alkyls and aryls. So transition metal alkyls and aryls, they have been prepared by four major methods. So they are given below with some examples. First is metathesis. So metathesis, in particularly by this process, organolithium, organomagnesium, organoaluminium, organotene and organozinc reagents, they react with metal halides. So we have come across different types of organocompounds, but mostly the organolithium and organomagnesium, that is a Grignard's reagent, they are strongly carbanionic, but the other main group organometallics like the organoalkyl, organozinc or organotene, they are less carbanionic. So this happens by the equation which has been shown in figure in equation 4.10, 11 and 12. So here we have WCl6, that is hexachlorotungsten. Here methyl lithium, so it forms this complex plus LiCl. So this is called as mostly the metathesis reactions. Then the second process is called as the metallate alkylation reaction. So this category, it represents the reaction of the carbonylate anions with alkyl halides as it has been shown here. So this takes place from an R plus reagent, that is the electrophilic attack on the metal. So here if you see, this is MnCO5 minus, which reacts with methyl iodide to form the corresponding complex plus I minus. So you see we have an electrophilic attack on the metal. Similarly in the second case you can also see this is the electrophilic attack on the metal. So such type of reactions are called as metallate alkylation reactions. Then the third category is the metallate acylation reaction. This is also the same process, but it involves the reaction of carbonylate anions with acyl halides. So here we have the R reagent of the R plus with the alkyl halides, and here metallate acylation reaction means the reaction of carbonylate anions with acyl halides. So here one example has been given. So here for this cyclopentadienyl complex, we have CH3CO, Cl. Then in presence of H nu, we form our desired complex is formed. Then the fourth category, the fourth process by which we can prepare organometallic compounds is the oxidative addition reaction. So first is with alkyl halides, a 16 electron transition metal complex, it undergo oxidative addition. So here for this iridium complex, by reaction with methyl iodide, it forms a complex of this type. Platinum complex, platinum halide with reaction with methyl iodide, it forms a complex of this type. Now this reaction occurs whenever a metal fragment, that is LNM, is inserted to the XY bond after breaking the XY bond. So we have this complex. This XY bond is first inserted like this into the complex. So here osmium here the oxidation state is 0, total number of electrons is 6, and the coordination number is n. But after this xy is inserted, that is the oxidative addition, the oxidation state of the metal is 2, total number of electrons present in the system is 18, and the coordination number now changes to n plus 2. So often some of the examples for xy can be like hydrogen hydrogen. Here some of the examples have been given. So often carbon like mln fragments they are found, as there is some similarity of inserting those fragments to xy bonds to inserting any organic carbon, such as we have CH2 into a CH bond or a SiH bond or a OH bond. So the oxidative addition, whenever we see, then oxidative addition is happening. In the first case, the coordination of the oxidation state was 0. Then after the oxidative addition, the oxidation state increases to 2. So here the metal fragment the oxidative addition, it increases by 2 units, by 2 units of the oxidation state, the coordination number and the number of electrons. So here you can see there is an increase by 2 units for the oxidation state, the number of electrons and the coordination number. So the metal fragment will be able to undergo oxidative addition only if it has a stable oxidation state of n plus 2 starting from the n. So this is means that the metal fragment must have electron with 16 or less. So in certain cases we have seen that even 18 electron complex, they can first lose a ligand or 2 electron, and then they can also undergo such oxidative additions. So here example has been shown. We should now understand that oxidative addition is just the reverse of reductive elimination. So here xy bond, this is the carbon molecule, this is a 6 electron. When the xy bond is oxidatively added, it is 8 electron, the coordination number is 2. Here the coordination number becomes 4. So here a classic example, it has been shown, that is called as the Vasquez complex. So here this is the Vasquez complex. This is a iridium complex where PPH3, that is the phosphine group, is present, and Cl and CO they are present. With the addition of MEI, the oxidative addition occurs, and this is the complex that has been formed. So with the same, Me is added here, this is I. So this is the oxidative addition for the Vasquez complex. Then the fifth method by which we can prepare organoalkyl compounds is by the process of insertion. So this alkene insertion is called as hydrometallation. So this process is widely used, and this is called as hydrometallation. So here it means that the insertion reaction between the metal hydride and the alkene, like here it has been shown in figure 4.20. So if we take the metal halide and we have the alkene, so they form, that process is the insertion. So here if we have this complex, then we add C2H4, then here we get something like this. So this is the addition of an olefin, that is C2H4, to the MH bond. It is included in this category. We call it as alkene insertion or hydrometallation. Then the insertion reaction also talks of carbene insertion. So here the metal hydrides, they react with carbenes as shown in these reactions. This is CpCO3 molybdenum H, and this is the carbene CH2N2. So which reacts, metal hydrides, it reacts with carbenes to form such type of complexes. So this is also an example of carbene insertion. So nucleophilic attack on the metal can take place to form an alkyl, often when we take a Grignard reagent or organometallic reagent, organolithium reagent, it reacts with a metal halide or cationic metal complexes. So in organometallic chemistry, that is the reaction of methyl lithium with Me2CO or of trimethyl nitrogen with MEI, these pathways, they are used to make bonds, that is they are used in the preparation of carbon to nitrogen bonds. So when an alkene group is transferred from one metal, that is zinc, magnesium, or lithium, to another. So a transition metal, for example, to another transition metal, then we call this process as transmetallation. So here the CO may be lost, but we also find this process, transmetallation, has also been found to be very useful in analytical chemistry. So when with the route of insertion, an alkene and a metal hydride may together form an alkyl. So here in this figure, it has been shown that C2H4 insertion is reversible, whereas C2F4 insertion product is formed irreversibly, because the MC bond strength is with the higher in comparison to the that of C2H4. So here an example that has been shown. So also in equation 4.27, we can see that the vacant site that opens up on the metal, it may be filled with another ligand which may be inserted, and thereby the alkyl metal complex may be trapped. This is how we have talked of earlier. Now we also find that additive oxidative addition is just an insertion of the metal ligand into XY. So insertion is particularly in organic chemistry, organometallic chemistry, it means of insertion of a ligand to an existing MX bonds. And here it insertion of alkynes into MH bonds has been shown here in equation 4.28. Then coming to bridging alkynes and other related ligands. So now we'll talk of bridging alkyls and its related ligands. So we know bridging ligands, that is mostly 2C2 electron bonds or 3C3 electron bonds, they are formed between the metals and carbon. So here in example this 4.16, you can see various types of bridging ligands has been shown. So in the first figure, that is 4.16a, so the bridging ligands of the main group elements, such as for aluminium particularly, this has been shown here. So there is a sharp resonances for bridging and terminal ME groups in the NMR spectrum. So even for 16 figure 4.16b, this is an agostic CH bond. It is the preferred route to bridging. So we also have a this metal they are present here, but the bridging is done through the agostic CH bond by this. It is then also in figure C, we have a planar methyl coordinated to D0 of the metals. That is, here we have a planar CH3 group that is coordinated to two types of metals, and it may also on either side of the plane. So these are the three types of bridging ligands that we can see. So then coming to alkylidines and carbides. So we'll just take a break of 5 minutes and then again resume with this part. So this part is alkylidines, alkylidines, and carbides. So two normal covalencies, particularly of the alkylidine, one to each metal. Here in figure 4.18, we see that as alkylidine is the Cr2 group. So in complexes like Cp2Ta, CH2Me, the alkylidine group, it forms a double bond to the metal and acts as a terminal ligand. Even alkylidine, that is Cr, they may act as a terminal group with the M triple bond C ligand. So finally, when we have a carbon, it can bridge to four metals, like the one here it has been shown in figure 14. Carbon is, it can bridge to four metals. In case of CHGOAC4, we find it is more common in clusters. So here in the example, it is mostly, here it has been shown it exists as a 6 coordinate. Then is metallocycles. Cyclic dialkyls, that is MCH2M, they are called as metallocycles, where MCH2 is present in polymeric number. Although metallocyclopropanes, that is N is equal to 2, it behaves like a metal alkene complex. The higher homologous, they are more like the dialkyls. They show interesting rearrangement reactions. Here it is a metallodialkyl. Here it has been shown and how the rearrangement reaction they undergo. So we should also note that the beta carbon hydrogen bond of this cyclic dialkyls is held away from the metal, that is the beta CH group. The bond, it is held away from the central metal atom, and so it is not available for beta elimination. So when we look into equations 4.29 and 30, we see beta eliminations, it involves a beta CC bond, because the CC bond of the beta position, it is more close to the metal than that of the beta CH bond. So we also know from metathesis that it converts propene to butene and ethylene. So the key step for this reaction, here it has been represented in this reaction. So and also in equation 4.31, it has been shown that cyclic diaryls which becomes very stable after this. So it has been also been found that the compound is, this compound is a 5 coordinate member with distorted Y geometry. So empty pi orbitals are also present in aryl, vinyl and acyl ligands. So because empty orbitals are present, they have the capacity to accept electron density from the metal center through forming MC bonds. Pentahalophenyl ligands, they are exceptionally stable and they are strongly bound. Vinyls and alcyls, they also have alternating bihepto bonding mode as shown in figure here 4.21. So the electron count goes from 1 electron to 3 electron. So the bihepto forms are probable intermediates in the cis-trans isomerization of metal vinyl complexes. Here it has been shown. Then less familiar, low valent sigma bonded organometallics. So we have seen from the case of main group elements that the highest valency is shown by the, generally is the same number as that of the group number to which they belong. Also, they have a set of lower valencies which differ by 2 units. Whereas for transition metals, the difference between their valencies is 1. So this difference of the valency is because of the inert pair effect, which we know that in by this effect the s electrons, they cannot take part in bond formation. So this may be due to the decreasing strength of bonds on descending a group. For example, the transformation of M2 to M4. So here the energy gained from formation of two additional bonds, it does not compensate the required promotional energy. So here it has been shown. So some representative structures of organoselenium and organotellurium halides have been shown here. Then bivalent organometallics of silicon, germanium, tin and lead. So organometallic chemistry, or they have particularly are highly dependent on bivalent organic species. So that is, so bivalent analogs of the heavier main group four elements, they have been researched. The bivalent organometallics of germanium, tin and lead have been also studied. So what, how is the preparation? So first is by the pyrolysis. So preparation of the given below is the silylene by pyrolysis of silane. So here this is a silane. It undergo pyrolysis at temperatures more than 200 degrees centigrade, and the corresponding silylenes are formed. So then the ring contraction reaction of cyclic polysilanes can also take place. So here this is how the cyclic polysilanes it occurs, and they form the silyl radicals. So these silyl radicals then they undergo to form the our silylenes. Then is the by the process of reductive elimination. So dehalogenation reactions they provide another route for generating SiMe2. So by this reaction you can see the SiMe2 is generated. So the SiMe2 this undergoes insertion reaction or addition reactions to form different types of products. So here SiMe2 has been shown, and the various types of reactions it undergoes to form different products has also been shown here. Then is the metathesis reactions. The simple alkyl or aryl stenylines, they originally called formulated as SNR2. They are actually linear branched or polystenanes, and they have been prepared by the following steps. So here the R is a sterically demanding ligand, for example like CHSIME3. Reductive elimination and metathesis reactions can lead to form stable and isolable subvalent organometallic derivatives by as shown here in these reactions. The metathesis reactions when used for synthesizing dialkyl germanium derivatives from GeCl2 and its complexes, as well as sterically hindered derivative using GeCl2 that did not give gold yield. It was found that the first complex with lithium and GeCl2 dioxane with this compound gave the desired product. So depending on the type of the reagent, the desired product can be obtained. The synthetic procedures for tin metallocycles have been shown here. So equation 4.48 we can see how we can prepare the in this equation tin derivatives have been shown here, and also lead derivatives dialkyl lead derivative can be prepared by this method. Then the structure and bonding. So the lead and tin derivatives they are moderately soluble in hexane, benzene or diethyl ether, but the germanium analogues they are very poorly soluble. Even though germanium and tin derivatives they are air sensitive in solution, they may be handled in air, but the lead derivative cannot be handled in air or in solution. So here this is the SnCl4 and the different routes to prepare tin to metallocycles. The ground state valency for the electronic configuration of germanium is Ns2 Np2, and these elements thus they form bivalent organometallics because with the help of two unpaired electrons that is in Np2. The sp2 hybridization of the valence shell electrons it also happens, and here it has been shown in figure how the sp2 hybrid orbitals they lead to formation of bivalent organometallics. Now, when we go to the fourth main group elements, the bivalent derivatives have both an MTP orbital and also an orbital containing lone pair of electrons. So, both Lewis acid and Lewis base behavior may be expected from them when they take up the ligands. So, here we from the scheme 4.2, you can see the chemistry of the bivalent group metal alkyls which have taken this group as an example. So here the scheme 4.2 here it shows the different types of reactions. So now coming to here in this scheme 4.2 of this organotin complexes, although this organotin complex is monomeric in cyclohexane solution, the crystal structure it shows dimeric structure. So the dimagnetic nature of the solid also confirms that there is no single tin-tin bond. So that is why if there is no single direct tin-tin bonds, then how does the compound look like? This is the bent tin-tin double bond, and this is how the compound looks like. So the complexes even such like tin complexes of this type they also have this type of structure. So now coming to fluxional organometallic compounds. So fluxional organic compounds, will take an example of uh, here, this is C5H5 whole 2, that is dicyclopentadienyl, and this is also dicyclopentadienyl titanium. So the crystal structure of the molecule, it shows 2 monohepto. Eta 1, it represents monohepto, and eta 5 represents pentahepto. So from this structure we can say it represents 2 monohepto and 2 pentahepto cyclodipentadienyl rings. The proton NMR of the molecule, it shows a single line. So in to understand this, we show that there is a interconversion of the different groups in the molecule. Here it has been shown how the migration of ion in solution, it takes place. So here, this, it was studied at lower temperature that this interconversion between the mono and pentaheptoligand, it occurs very slowly. But even at such low temperature, a dynamic process of the monoheptoligand, they also occur. So fluxional processes are those that involve acyclic saturated hydrocarbon rings, such as alleles and allenes. They are also very common. So example is the pi complex that is formed between tetramethylallene and tetracarbonyl iron. Even the proton NMR is also supportive of the data. So whenever we see a migration of iron complex of the ligands, so that is leading to a dynamic process, then such type of compounds, we call them as fluxional organic compounds. Then is organo copper compounds and its applications. So organometallic compounds having copper that is bonded to the carbon atom, they are called as organocopper complexes. That is copper carbo, the compounds which have copper to carbon bonds. So it was first discovered by Gilman, and we call it as the Gilman reagent. And these are the organocuprates compounds. They are widely used in organic chemistry. So copper belongs to group 11. It exists in Cu0, Cu1, Cu2, 3 and 4. But the 0 and 4 species are very rare. So whenever we will talk with Cu1 and Cu2. So Cu2 state is the most found in inorganic and coordination chemistry. So this state we will be mostly dealing with the Cu2 plus state in the organometallic complexes of copper. The stability of copper compounds. So organolithium compounds, they are much more reactive than the organocopper compounds. But the organocopper compounds, they are thermally unstable. So the R group, it acts as the nucleophile and attacks the various electrophiles. The thermal stability of the this such type of organocopper compounds, they can be increased by substitution of hydrogen atoms by fluorine in the organic moiety, by addition of other ligands such as phosphine or amines, and by the use of substituents having heteroatoms which can provide additional intramolecular coordination sites to the metals. So lithium dimethyl cuprate is an organocopper compound. It is prepared by mixing methyl lithium with Cu2I2, that results in the formation of the lithium dimethyl cuprate. So some of the particular characteristics of this reagent is that compared to carbonyl group, it can take part in numerous reactions because it has a strong nucleophilicity towards carbon atom. It does not react with any cyano or ester group. It prefers to attach to the beta carbon in an alpha beta unsaturated carbonyl system. Any halogen atom, they may be replaced by methyl group by this reagent. Then is the halogen substitution. By interaction with organic halides, it forms CC bond and they prefer ether or similar solvent. Here LiCuR2 plus R dash X, it forms R dash plus LiX plus CuR. Then alkene complexes. Copper is the only metal that is involved in biological complexes, and it reacts with ethylene and copper complex to form this type of complex. So this particular complex, it acts as a hormone in different plant reactions, and it has also been isolated. So then chelating agents from non-bornadine or cycle polyenes from crystals has also been isolated. Then is the acetylene compounds. Copper 1 chloride is concentrated in HCl, it absorbs acetylene to give a colorless compound like CuCl, C2H2, and CuCl2, C2H2 minus. So these halide solutions can also catalyze the conversion of acetylene into vinyl acetylene or to vinyl chloride. So copper 1 acetylides, they provide a useful route to the synthesis of variety of organic acetylenic complexes. So an in particular important use where acetylides are probable intermediates is the dimerization of acetylene. So this is where copper 1 acetylide is used. Then carbonyls, simple carbonyls, they are not stable in nature. Thus the CuClCO, it exists under CO pressure. So at a pressure of 1 atm, the following reaction has been obtained. So here it has also been reported that CuCO3 plus and CuCO4 plus have also been that are formed in the reaction. Then for the formation of hydrides, various types of methyl cuprates, lithium methyl cuprates react with lithium aluminium hydride to form such type of hydrides of copper complexes. So this is all about the different types of organometallic alkyls and organotransition metal alkyls and aryls. So now starting with metal carbonyls. So we know that CO or carbon monoxide is a very widely recognized metal, and that has been widely popular for formation of metal carbonyls. So first, the CO, it strongly binds to the metals to form the complexes. Most of the time the oxidation state of is zero, and sometimes also that is very low oxidation state, but it has been found that most of the metal carbonyls that are formed, they generally follow the 18 electron rule, so or the effective atomic number rule. So many compounds that have been prepared from transition metal carbonyls. Transition metal carbonyls is in itself a different topic of organometallic chemistry. The carbon monoxide, it undergoes substitution by various ligands, and the carbonyl group, it stabilizes the molecule whenever it undergoes oxidation as well as thermal decomposition. The electronic and molecular structure of the compound can also be determined with the help of the CO ligand. We know for the first transition series, the sum of the stable complexes, here it has been shown, table 5.1. Here it's- Anyways, so preparation and properties of metal carbonyls. So first is nickel carbonyl, which is directly formed by the combination of nickel with CO with a certain 1 atm pressure and 25 degrees centigrade. Even iron pentacarbonyl can be formed by the direct combination of the iron with CO. Nickel tetracarbonyl is very nice. It is very toxic and colorless, and it is also very sensitive to. It is the basis for the used by it is extracted by the Mons process. So then is the second preparation is by the reductive carbonylation method. So in this method, the carbon monoxide, it acts on a metallic oxide, halide or other compound. Here it has been shown. So majority of the carbonyl complexes, they are formed when the metal is reduced in the presence of carbon monoxide. So here you can see chromyl chloride plus aluminium plus 6CO. In presence of AlCl3, it forms the hexacarbonyl chromium. Similarly, Re2O7, in presence of 17CO, it forms the Re2CO9. So this is called as reductive carbonylation. Other methods of preparation, they are illustrated by the following examples. We can see how this is VCl3. It reacts with 6CO in presence of diglyme to form this VCO6, ultimately to form the hexacarbonyl vanadium. So this is also one method. So here also polynuclear carbonyls, that is the carbonyls where more than one metal atom is present, they are called as polynuclear carbonyls like Fe2CO9. It is obtained by the photolysis of FeCO5 in acetic acid. So polynuclear carbonyls, they may be obtained by thermal or by complicated decomposition of carbonylate anions in alkaline media. So some of the examples, it has been shown here how they are obtained in alkaline or other media, like here the medium maintained here, it is THF, and here it is a very complex process. Then what the 18 electron rule? So what is this 18 electron rule? This is particularly very useful for metal carbonyls, and this is also we generally regarded as the effective atomic number rule. So the first carbonyls that was first discovered to be that of iron, cobalt and nickel. So when their formula was these metals and their carbonyl complexes, where the formula was decided for them, it was found that they conformed to the 18 electron rule. Now this rule can be formulated in a very simple way. First we need to calculate the total number of electrons that is present around the metal, and in most cases it has been found to be corresponding to that of the noble gas configuration. That is, suppose most 36, 54 or 86. So 36 is for krypton, 54 is for xenon, and 86 is for radon. So these metals, they now they have, then once the total number of electrons becomes equal to that of an inert gas, the atomic number of an inert gas, then we say that the metal carbonyls, they obey the effective atomic number rule. So this is effective atomic number rule. The complexes of transition metals with pi ligands and their organometallic compounds, they generally obey the EAN rule. The central metal atom, it appears to have acquired the configuration of the noble gas by the transfer or the sharing of electrons. So the total number of electrons which the metal ion appears, it is to around itself, is called as the EAN, and this should equal the 36, 54, 86 for the EAN rule to be followed. So we also say when the metal, it achieves an outer electronic configuration like N-1 D10 NS2 NP6, then there will be 18 electrons in the valence shell. So once 18 electrons in the valence shell, it indicates a closed, a stable configuration. So this is also called as the 18 electron rule. So there is also another way of saying this is all, that all the bonding capacity of the metal is utilized. So once a metal carbonyl, it occupies, it follows or obeys the 18 electron rule. So this indicates that the all the bonding capacity of the metal, it has been utilized. So this rule, it allows the systemization of much of the structural chemistry of transition metal organometallic compounds. The transition metal complexes that are studied, they contain metal oxidation states of +2, which are N or O donors. So here mostly when we talk of the carbonyls particularly, then the metal is in very low oxidation state, and mostly we will see that they are present in zero. So zero oxidation state. So we know that when bonds are formed, there is a change in energy. So particularly for positive oxidation state, which is greater, for the oxidation state when it is positive or higher than 2, then the effective atomic rule does not hold good. In certain cases, the molecules having 16 valence electrons, they are also found to be stable. So this is particularly true for metals like rhodium, palladium, iridium and platinum. Now these complexes, they are, although they contain 16 electron rule, they obey, so, and they have been found to form 4 coordinate complexes. So in most cases, the maximum coordination number is 6, and if each ligand donates one pair of electrons, then the metal must have D6 configuration to follow the 18 electron rule. So we'll find that the second and third row transition metals, they form a number of compounds like MoCO6, Tc2CO10, Re2CO10, which are similar to the ones that has been shown in the table. So also nickel tetracarbonyl, that is, it is stable but only at low temperatures, but palladium tetracarbonyl is has been found to be stable only at room temperature. So here, although the molecular formula remaining the same, the properties, their physicochemical properties, they differ. So this is also because when we do go down the column, then the strength of the metal metal bond increases. So like for both binary complexes of ruthenium and osmium, it has been found that the stability is the greatest for trinuclear complexes. So this is how the stability of the metal carbonyls is ascertained. Then how can we count the total number of electrons that is present in metal carbonyls? So for this step, two or three steps they are required, and it is very easy to calculate the effective atomic number of the metal carbonyls. So in the first case, we will calculate the valence shell electron configuration of the metal. So then we will look into the charge of the complex, and looking into the charge, we will add electrons or we will subtract electrons. Second, we will calculate the number of the electrons that is donated by the ligand. Since we are talking about metal carbonyls, so the carbonyl atoms that is donated, but that it always donates two electrons. So here in CO, the it ligands two electrons, and each bridging ligand it contributes one electron to each metal. So for when we talk of carbonyl ligand, two electrons are donated. So then if any conventional ligands are present, then we will also check the number of the electrons that are present to it. Suppose we have a MM bond, then we will write it donates one electron. So find out how many. We will, after finding out the total number of electrons, we will add all of the electrons, and then we will check whether after adding the total number of electrons, it it follows the atomic number of any inert gas or not. So metals with odd electron, they cannot satisfy the 18 electron rule just by simple addition of CO ligands. So there are several options to these metals by which the 18 electron rule can be satisfied. So the simplest is by forming a carbonylate anion, that is MCON minus. So when we have an odd electron metal atomic number, for the metal, then the carbonylate anion it satisfies the formation, the effective atomic number rule. So here MnCO5 minus. So with one example it has been given. Mm, Mn is 7 electrons, the 5 CO, it is because the 1 CO it contributes 2 electrons, so 5 CO it contributes 10 electrons. The charge here is 1 electron, and that is the total is MnCO5 minus. Here this is an anion, so the charge is 1, and the total electron that is satisfied here is 18. So MnCO5 minus, it obeys the effective atomic number rule. Similarly, for CO, that is cobalt tetracarbonyl, cobalt tetracarbonylate anion, for cobalt, the valence and electronic configuration it is 9 electrons. The 4CO they donate 8 electrons, the charge is 1 electron, and the total counting is 18 electrons. So this is how we calculate the total number of electrons for a carbonylate anion. Now we will consider how to calculate the EAN for a dimeric species here. For example, Mn2CO10 and CO2CO8. So for 2Mn, we know that for per single Mn, the total outermost electronic configuration, it is 7 electrons. Since 2Mn is present, it is 14 electrons. Carbonyl, 10 groups are present, so 10 into 2, 20 electrons. Then we have a metal-metal bond, that is MN-MN bond, so it will give 2 electrons. So total we see for the molecule Mn2CO10, it is 13 electron. Then for each Mn for each Mn it is 18 electrons. So here this also occupy, it also obeys the effective atomic number rule. Similarly, we also find CO2, CO8, it also gives obeys the 18 electron rule. So this is how we calculate the total number of electrons, and then we see whether it occupies the 18 electron rule or not. So now let us use the 18 electron rule to find the value of n in the, for this is a complex, it has been given, and we see we have to find out the total number of carbonyls. So here we have, see, this is cobalt, two electrons, two cobalt, two atoms are present. So this is for one cobalt, outermost electronic config, outermost electrons is 9. So for two cobalts it is 18. So we have NCO. Now for one carbonyl, two electrons are donated. For n number of carbonyl groups, two n electrons are donated. We also have metal metal bond, that is cobalt cobalt bond, so two electrons. So overall this should be 18 plus 2n plus 2, this is equal to 36, and then n is equal to 8. So using this formula we can also calculate the value of n for any complex. So this is in table 5.1. It shows the total counting, the contribution of the ligands in counting. Suppose we have metal carbonyl. Metal carbonyl, it contributes 2 electron. Thiocarbonyl, that is the CS, it contributes 2 electron. Phosphine 2, amine 2, dinitrogen it is 2, dihydrogen is 2, alkene is 2, alkyne is 2. But when we talk of nitrosyl, if it is present in bent structure, then it is 3. And nitrosyl, if it is present in linear structure, it is 1. Halogen is 1. Hydrogen is 1. Alkene is 1 electron. Acyl is 1 electron. As you can see, then we have monoheptoallyl, it is 1 electron. Triheptoallyl is 3. Cyclopentadienyl, if we talk of, it is 5. This we should always remember. For benzene, it is 6. Cycloheptatrienyl, that is tropylium ion, so here it is 7. And cyclooctatetrienyl is 8. For a bridging ligands, it is 2. When there is a metal metal bond, there is, it is 2. Halogen, when it is present in between two metal atoms, so here the contribution is 3. Alkyne, in such type of case it is 4. Hydrogen, if it is present between two metal metal, it is 1. Alkyl is 2. Amide 3, if it is present between two metal metal. And phosphide is 3. Alkoxide is 3. So this is how we have to remember the different neutral atom electronic count for different types of ligands, which will help in the calculation of the effective atomic number rule. Then in this table, we will see details of some common ligands that is found in organometallic compounds. So for hydrogen, the electrons donated is 2. Fluorine, chlorine, bromine, the charge is -1, the electron donated is 2. For carbonyl, the charge is 0, but the electron donated is 2. For cyclopentadienyl ion, the charge is -1, but the electrons donated here it is 6. For eta 6C6, the formal charge is 0, but the number of electrons donated is 6. So these are some of the examples that we have to remember. Then there are also certain exceptions to the 18 electron rule. Sometimes the molecules with 16 valence electrons, they are stable or even more stable than the 18 electron molecules. Such cases, they are found to be true to the metals at the bottom right of the corner of the transition metal series, like rhodium, palladium, iridium and platinum, which have no inclination to become 6 coordinate molecules, uh, and they form 16 electron molecules. So these type of complexes, they have d8 metal atoms, they also have d10. So here the iridium platinum complexes have been shown which do not follow the 18 electron rule. So it is not always mandatory that the 18 electron rule has to be followed. We also come across different complexes which do not follow the 18 electron rule. So some intermediates in reacting organometallic chemistry, but they have been conformed, like PTCCPH2 a 14 electron bis acetylene platinum 0 has been found, which is an exception to this rule. Now, some of the electron, only some of the electron, 16 electron complex is stable. So how we can say this 16 electron complexes are stable? So we will consider M D as the ligand. For a D8 configuration, square planar is not discriminated. So 16 electron, that is D8, they have similar chances of that of a 18 electron rule. Now we will consider NO. This is a peculiar case because NO is a odd electron molecule which possesses a nitrogen lone pair, but also there is one electron in the pi star MO. So our convention to treat MO as NO plus. We always treat NO plus with the extra electron that is counted among the metal. So other conventions, we can write it as a 3 electron donor NO minus, but we mostly write it as NO plus. However, the convention used here is based on NO plus to CO, Cn minus and N2, which constitutes the isoelectronic species. The NO plus ligand will involve its pi star MOs with the metal d pi atomic orbitals to a certain extent, and some net electron density distributed between the metal and the NO plus pi star, that is independent of electron counting devices. So here MnCO4 NO complex. This is tetracarbonyl nitroxyl manganese. This is, in this case, the we have NO plus, that is 1 sigma pair, 4CO is 1 sigma pair, Mn minus is 4 pairs, total 9 sigma pairs of electrons, that is 18 electrons. Similarly, for dicarbonyl dinitrosyl iron, we see 18, it also follows the 18 electron rules. Now let us return to some of the convention, counting electron counting convention. The ligand which we have cyclopentadiene, that is it monoheptocyclopentadiene. So here the structure it has been shown. So here what we see, the eta 1 of the cyclopentadiene, it has been shown in figure 5.2. We can see, and thus it is this pentaheptocyclodienyl, that is eta 5 Cp, we write it as eta to the power 5 Cp. It is one of the most important ligands, and it has so 5 carbons equidistant from the metal. So this is the structure of the pentaheptocyclodienyl structure. So in this structure, the ligand acts as a carbanion and 3 pair pi donors. It has been shown here like this. So for this particular structure, it has 2 CO pairs. 2 CO in this, we have 2 CO. So this is 2 sigma pairs. Eta C5H5 minus is 3 pi pairs. Eta C5H5 minus is 1 sigma pair, and Fe2 plus is 3 pairs. So total 9 pair of electrons. So another 3 pair has been, for this system, it has been seen here. We have 2 benzene rings. So this is 6 pi pairs, and for the chromium it is 3 pairs. So total 9 pairs. This is how we calculate the different the 18 electrons for different system. Then here, like cyclopentadienyl, it contains odd number of electrons. We also have here the resonance structures of the allyl radical. Here you can see this is the resonance structure of allyl radical. Also, for in certain allyl complexes, we can also calculate the different pairs. So an example of a di in metal complex, here it has been shown FeCO3 eta 4 C4H4. The interesting hydrocarbon, this is say cycloheptatriene. Here it has been shown. It is an isomer of norbornadiene, and it has a flexibility to donate different donor pairs. So some of the structures it has been shown here for such type of complexes. These are some stable binary carbonyls that has been shown in this table 5.3. For the first transition series, vanadium, chromium, manganese, iron, cobalt, nickel, you can see. For the second transition series, the stable complexes are of that of MOTC, ruthenium, again Ru3, rhodium, RH4. Third transition series, we can see the iridium, it forms IR2, IR4, IR6. So these are all metal carbonyls, they are solids. Exceptions are the monocarbonyls or the iron group and nickel tetracarbonyl. Then for the nickel tetracarbonyl, it has a tetrahedral structure that we know. For binuclear carbon, the iron FeCO5, it has a trigonal bipyramidal, and CrCO6, it has an octahedral structure. For binuclear carbonyls, binuclear means they have a double MM double bond. So here, for different the stretching frequencies of different metal carbonyls, that is determined from FTIR, it has been shown here in for 2143 centimeter inverse, it is for free carbonyl group. For the terminal carbonyl group, it lies in this range. For double bridging, lies in this range. So with different types of carbonyl groups that is present in different environment, it shows different IR stretching frequencies. So the for a binuclear carbonyl, here Mn2CO10, this is the structure that has been, the condensed structure here, it has been shown here for Mn2CO10. Similarly, this is the structure for Fe2CO9. So both it has for this Fe2CO9, it has both bridging and terminal groups, and the Fe here, each Fe is joined to three bridging groups, and the three CO groups by a coordinate bond. CO2, CO8, the structure, the isomers of CO2, CO8, it has been shown here. And these two isomers, they are in equilibrium with each other. Accordingly, we can calculate the total number of electrons that are present in the above carbonyls. So with this is all about your carbonyls. We'll start with the bonding in carbonyl compounds in tomorrow's class.
Natural chemical factor. Circle.